Thanks for joining. I'm Lisa Despin. I'm a postdoc here at the Complexity Science Hub at the Network Inequality Group. And today I have the pleasure of having Ana Stoica here with us. She is a research group leader in the Social Foundations of Computation Group at the Max Planck Institute for Intelligent Systems in Tübingen. Her work focuses on social foundations in network systems, such as algorithm design, fairness and inequality, evaluation methods, and causal inference under interference. Ana holds a PhD from Columbia University and a bachelor's in mathematics from Princeton. Since 2019, she has also been co-organizing the Mechanisms Designs for Social Good initiative and is a co-founder of the ACM conference series on equity and access in algorithms, mechanisms of optimization. I'm very happy that Ana is here because we are working on similar related topics about fairness in social networks. So Ana, the floor is all yours.
All right, thank you so much, Lizette, for the kind introduction, and thank you all for welcoming me here. It's really nice to see a lot of you here, and I'll be following a lot of your work in networks too, so it's really great to get to share a little bit of what we've been doing lately and get some feedback from you. Today, I wanted to chat about our recent work in fairness in link analysis ranking. It's about HITS and PageRank on homophilic networks. We presented this work earlier this year at a web conference in Singapore, and this is joined with Nelly Lidwak and Augustine Chantrot. Nelly is from the University of Twente in the Netherlands, and Augustine is my PhD advisor from Columbia University. So to start with a bit of motivation, I think, as I think a lot of you work on this kind of topics, there is an increasing concern that algorithms may increase discrimination for certain groups of people. And this happens in a variety of applications, such as in higher algorithms, where minority groups may not get the same kind of opportunities or referrals as everyone else. Similarly, in the way online platforms displays ads and content for people who are looking for jobs, differentiated by groups as well. Similarly, also in housing, the way people get access to housing or opportunity to apply for housing. And finally, in education and as well as online platforms, there's recent evidence that search results even affect hiring decisions as well. So there's this concern that we think about discrimination with respect of different demographic groups in society and the role of algorithms to amplify or recreate this kind of inequality that we see around us as well. I focus a lot in algorithms that use network features, and in this kind of realm, what really matters is how well you are connected and who you are connected to. So the more central you are in a group, the more likely you are to get opportunities, and for this kind of information to get fed as features or signal in different algorithms that will use this and therefore promote different kind of opportunities for yourself as well. This work is focused mostly on link analysis ranking algorithms. The most famous ones that we've thought about that some of you may know are PageRank and HITS. Both of them developed concurrently in 1999, and they use the network structure to create this relevancy ranking for mostly search engine. So they're oftentimes used for as features for recommender systems, etc. So they're considered a way to think about centrality in networks in which the more central individuals are being ranked for the purpose of a search engine, or that centrality is being fed as a feature in other applications such as, say, recommendation systems. The most famous one that maybe some of you may know is PageRank. It's used in the Google search algorithm in personalized PageRank, general PageRank. There's many ways to think about it or different versions of it. And the more central you are within other different entities that connect to you, the more likely you are to show higher up in the ranking. So the ranking score is basically a number that you get. The number itself maybe doesn't matter, but it creates a ranking among you and other entities, people, or queries that could be restaurants. It could be different kinds of search results in this web that will then be shown to the users who search for relevant queries. To give you a little bit of the background on this algorithm, so they all use kind of the network structure in different ways. And one way to think about PageRank is as random walks in a network. So the way it's computed is quite interesting, simple. You have a centrality metric or a centrality number at each time step that gets updated in the following way. That centrality vector is X. It's a vector that contains the elements of all the nodes in the network. And that will get updated at each time step through a transition matrix P. that is based on the network. This is the random walk that I'm mentioning. For example, it can be something as simple as just using the adjacency matrix and just like walking forward through the network. There's also a restart probability. In directed graphs, this doesn't really converge unless you actually restart at some point. So with some restart probability, you restart your random walk from some random place, and that random place is called V, whatever you start from. You usually just restart from a random position in the network. So an easy way to think about the intuition of this is just to say, count the forward paths, and the more likely you are to end in a forward path, the higher your centrality score is, because a lot of other entities on the network will reach you easily. It's something different than degree, right? Degree just looks at one hop. PageRank looks at actual forward paths and you look at the stationary distribution of that. If you just look at this kind of random walk in undirected networks without this restart probability, you do end up with a degree distribution. But in directed networks, you may not converge, and that's where the restart comes into place. So this was a simple algorithm developed originally. And you end up with a centrality metric that's slightly different than the degree because it contains more information that's aggregated from the pathways of your neighbors as well. An interesting algorithm that was developed at the same time I mentioned before by John Kleinberg is HITS. It's quite related, and it thinks about two kind of entities. It thinks, well, I don't only care about who is able to reach me through a forward path. I care how important they are based on how many degrees they have, what degree they have as well. So you think about two types of centrality: an authority node and a hub node. An authority node is someone who like spreads out a lot and aggregates a lot of connections from people. A hub is one that is basically a hub, so it will send a lot of connections to other people as well. So what matters here is that you have a good authority score if good hubs point to you. So you have a double update in which the authority score, each node could be both an authority and a hub. You get two numbers for each. You may be a good authority, but a poor hub if everyone points to you and you don't point to anyone. And you may be a great hub if you point to everyone, but nobody points to you, right? And you have a double update at every time step where the authority score of myself is the aggregated hub score of all of my neighbors, and vice versa for the hub score as well. There's a simpler intuition for this update rule. The intuition is that you just end up with the principal eigenvectors of the adjacency matrix transformed with itself. And we can think about this in the random walk example as well. In the PageRank, we're doing forward paths, and the more likely someone ends up from a forward path onto you, you have a higher centrality score. In HITS, you do backward forward paths. So you're counting how much, if you start from a backward forward path, like someone who points to you and then you point to someone else, and then you continue that backward forward process in directed networks, how likely you are to end up in that node. And that likelihood is basically your authority score. You can think of authority as the true centrality that we're comparing with PageRank here. The more authority you have, the more likely that you are central and relevant for people, and the higher up in this score distribution you will end up being as well. Is this clear so far for people? Great. So with this in mind, there's been a lot of recent evidence, especially empirical and numerical evidence, some of it that comes from this lab that I've been reading in depth as well, to think about how this kind of ranking algorithms affect fairness as well. On the empirical side, or on the even anecdotal side, there's been even older evidence from even 2015 by saying like, well, if you go to Google search and you look at images or results, the representation of different groups that you see, there is not really what you would expect in the population. So if you look at CEOs, maybe there's a bunch of CEOs who are women, around 11% in the population, but if 27% in the US population. But if you look at the Google image search results, that number is underrepresented. So somehow we lost some representation, and there's a sense that, well, what happened in the algorithmic side there? If the reality is that we have some representation, it may be good, it may be bad, but in the end, what we see in the online world got even worse. So it, in a sense, it got amplified from our expectation from society. And that's a concern. So this can be thought of as minority groups in this kind of ranking get pushed down even further than some sort of baseline that maybe we expected, and we can discuss what's a reasonable way to even think about this expectation. And some of the works that came from here think about deeply what kind of network models and structures lead to minorities being pushed down. I will talk about this because we're also thinking about a similar model that can act as a mechanism or explanation for what network structures actually push these minorities down under algorithms such as ranking. Another empirical result that's quite interesting, it comes from people from the psychology department that have studied this question in ranking. It's from a couple of years ago. And they did the following. They thought, well, let's look at different countries and let's measure the percentage of different search results in the image search among different groups. If you ask a question, a query that should be neutral with respect to the two groups. So if you look for like person or things like that, what is the percentage of different groups in the search results? And that percentage correlates. So the percentage of, let's say, like men or women in the Google image search results correlates with the gender index gap of the country in which that search was being done. So in a sense, this correlation tells you that there's a correlation between some measure of inequality, gender inequality in this case, in the country from which we're performing search, and in the representation of people under a Google search result within that country. So algorithms mirror society under this perspective as well. There's an effect of this kind of mirroring. We can think about mirroring, amplification. That's a bit hard to quantitative estimate, but this is some evidence that that's something we should look at. And they did take a further step, which was to say, what is the effect of this kind of results on people's perception, their hiring decisions, and so on. So they ran a randomized controlled trial, and they asked people in this study to look to decide whether different candidates were a good candidate for a job or not. Before this decision, they show people this kind of results. I mean, not this graph, the actual like results with pictures of people from Google search. They'll show them more equal results between different genders and more biased results with different representations of genders in the search results. So the interesting finding that they found, this is what I want to show, is that if you show people more diverse results, their decision for who is a good candidate for a hiring decision too is influenced by that, and they will also make more diverse decisions in who to hire. If you show them less diverse results, that will directly influence their hiring decision as well. So there's a hiring decision, the proportion of women that they chose, and the different results that they show them in the Google search case as well. Yes, there's a question. Oh yeah, so there's a series of images that they show them, and let's say for some, in one case, they show them a series of queries and the results of those queries on Google search. So a more diverse representation meant like, oh, the search results actually show like half women, half men. And in the unequal case, they show the Google search results show like 99% men, 1% women. And that would be a non-diverse case of showing them Google search results for different queries. And in that case, their decision to hire different candidates that they would get a profile form and think about like, is this a good candidate or not a good candidate, would be influenced by the association they had before as well. So there's this like, in the realm of psychology, there's this kind of like associative biases studies in which like what you see in perhaps one context influence your decision. And what they did here was basically to provide some evidence that what you see online will affect the decisions that you make that are maybe not online, maybe offline, but they will carry some weight onto you. So this kind of differences, we can call it bias or just some like non-diverse results will affect your own decisions too. If those results are biased, it's likely that you may be biased as well in the way you make decisions. Totally independent from the Google search results, exactly, yeah. Great, so this is the kind of motivation that brought us to our work as well, and to think about what exactly in the network structure that these algorithms use may create biases or may push these minority groups further down in the rankings that are provided by them. I want to start with a bit of empirical research here. So we look at different data sets, and these data sets have different kind of structures. all of them have, we looked at two groups. So in the APS data set, this is the American Physics Society. The nodes are papers in physics, and there's two groups, which are two subfields of physics, classical mechanics and quantum mechanics. And the edges are citation. So of course, this network is quite segregation. If you do classical mechanics, maybe you don't cite the quantum mechanics paper. It's quite natural. One group is larger than the other, and there's about 20-something%, 31% minority in one of the fields in the network as well. So we can simulate different kind of centrality metrics and see what ranking we get under those. The first one I want to show is just the degree, right? So if I just order the papers by the degree, and that's in orange, on the on the x-axis is the top x%. This is people, it's nodes, the top x% nodes, and within those, what is the percentage of minority? We can think of the two groups as say blue and red, with red being minority, and I'll show later in the model. So the percentage of minority within those top x% in the ranking. Maybe an easier visualization is here as well. Let's say you have two groups in your population, and these are, let's say, the two papers or two genders and so on. And in the degree setting, you may say like, well, who's in top 1%, who's in top 2%, and so on. So you look at the percentage of, say, the minority group in the population, in this case, red, among top 1%, 10%, 20%, and so on. And you look at their representation in the ranking provided by the degree. We can think about the degree metric, like the number of connections as you have, some sort of like societal metric, right? This is what we would consider in this study as some sort of baseline. This is what you have in the world. How you get that, I don't know. There's some process in which you made connections and it ended up with this. And the question we're looking at when I say minorities get pushed down is that perhaps there's evidence I will show you that the minority group depicted in red kind of gets pushed down in the ranking. So they will be shown lower and lower in the ranking. So this is the visualization I want to show you in these graphs. If you look at the top 100% in the far right of this graph, that's everyone in the network. So among those, of course, the percentage of a minority group is just the percentage of everyone in the network. So we start at the baseline, the dashed line, which is just the percentage of minority in the population, 31%. As you move from right to left on the x-axis, you move towards higher and higher places in the ranking, from top 100% people to top 50, top 10%, top 1%. This is in log scale, and so on. So we look at how the representation of people among this ranking changes as you move towards higher and higher rankings. It means that if you look at, like, say, top 1% of people, the representation of a minority is no longer 30%, of course, it's around, 15%, so it dropped to half from the original one, right? One way to think about inequalities is exactly this kind of statistical thinking. This is not the only one. Is to say, like, well, if the percentage of people drop as I go to higher and higher rankings, that means they're kind of underrepresented at the top of the hierarchy. Yep. So different data sets, different type of nodes. The American Physics Society is nodes are papers. And for the DBLP data, this will be people. For Instagram data, this will be people as well. I started with the APS data set, but maybe I'll mention what the other data sets are as well. The DBLP data, the nodes are people, and they cite each other's papers. And so it's maybe a bit confusing with the APS data too. And we have authors. Yeah, the gender is based on the first on the author of the paper. So each author has an assigned gender from the DBLP data set, and they cite each other. That means there's a link in the social network. There's about 22% minority, in this case, women. In the third data set, it's an Instagram data set where the nodes are again people. This is something we collected in our lab a few years ago. And in this data set, the nodes are people, and they connect to each other if they liked or commented on each other's photos. And there's about 45% men in this data set. Somehow they're in the minority. But the interesting part is to say that, well, actually, if you look at the baseline of what is the percentage of minority, in this data set, they're actually better connected. So the degree of the minority is actually above the baseline as you move to a higher and higher degree. The orange line here in top X% of people, then is the baseline. So that's the difference between Instagram and the other ones, is that the minority is better connected in terms of degree, whereas in DBLP and APS, the minority is actually worse connected in terms of degree as you move to higher and higher rankings. The DBLP data in particular, you can see a clear trend of just like going down. As you look at higher and higher rankings, the percentage of minority among those in higher and higher rankings just like drops to like pretty clearly to say 10%, up from 22%. So this was just about, I showed you this, we were looking so far at just the orange line, which is just the degree, right? This is some sort of like baseline. This is what happens with the degree centrality had you looked at that in society. That's one baseline we're looking at. If you compare this, the purpose of our work is to think about how do networks and these kind of algorithms compare to this baseline. So we run PageRank and HITS on this kind of networks, and then we rank people based on the scores that they got from PageRank and HITS centrality as well. And if you do that ranking, you do observe some differences. First of all, in the APS data set, it actually looks like it's a bit better. It improves the representation of minority towards higher and higher percentage of degree in the blue line, right? It gets closer to the baseline. So low is bad, but higher up near the baseline is good. Whereas HITS does a terrible job. Like it just drops it to literal zero. So it basically pushed all the minority that is above, say, like 5% out of the ranking. On the PLP data, that's not really the case. They're all kind of doing the same. It's not really a big difference. Whereas on Instagram, you see kind of an opposite trend, and this is an interesting one. And that is because, well, the minority is actually better connected than the majority. So the percentage of minority in among different ranks by the degree metric is actually higher than the baseline, right? And that actually gets amplified by HITS, but it kind of made a little bit more fair by PageRank as well. So some differences in this data set, that one mechanism of explaining this is, of course, the network structure. But what exactly in the network structure is explaining these trends and these differences? That's what we were looking to find out. And the elements that we found out were to think about the degree distribution as well as homophily. So homophily is the tendency of people to connect more with those who are similar to them. APS data that I mentioned before, you have these two clusters, classical mechanics, quantum mechanics, and they cite each other. They don't cite each other, they just cite themselves. Supercluster network, think of it as high homophily. In DBLP, it's actually quite integrated network. Men and women kind of cite each other interchangeably, and you don't really see like such a division of clusters. They're co-authors, they cite each other quite a lot. So that's one difference, and that's something that I'll explain using network models as well. But you can see it empirically here as well. Instagram dataset kind of has moderate homophily, so there is a tendency of men and women to kind of segregate a little bit on this social network, on this particular dataset that we collected. But it's not as major as on the APS dataset. It's kind of so-and-so. So you kind of see a moderate trend here as well. All right, so basically, yeah, this was the question I mentioned, what explains this behavior in PageRank and HITS. And our work was trying to find evidence for when this kind of bias in representation gets amplified or alleviated in networks. So the network dynamics that build our model that we found are some explanation for this are, first of all, inequality in the degree distribution that leads to bias in ranking as well. We saw this empirically on the data set. Few people connect a lot, and most of the people are not that connected. That's something that we see in a variety of network data sets, online, offline, and so on. Homophily, the tendency of people to connect more with each other than across. And this is, we get a signal, both empirically and in theory, that more homophilic groups actually make PageRank better for the minority, but make HITS really, really bad. It makes HITS really push minorities to the bottom. We're going to use a generative network model in which we have evolving edges and nodes that come into the network and connect based on a model as a mechanism to explain how these factors affect PageRank and HITS as well. So I want to talk about the model. I'm going to introduce the model. It's called the bias preferential attachment model. It's quite similar, very similar to some of the models that Lisette and Fariba have used so far, also in this kind of studies in recommendation and ranking. So it might look quite familiar to some of you. I've seen it first in this paper from Avin et al. In 2015, when they thought about how citations how citation networks are quite unequal between different demographic groups as well, and how we can explain that. So the model ingredients are the following. There's two groups of people. You can think of notes, people, papers, as we saw before. There's a majority and a minority, and we can think of them as having two colors, blue and red, with red in the minority. There's a preferential attachment dynamic in which new people come into the network at every time step, and they connect with probability proportional to the degree of the people who already exist. So this is called preferential attachment, or it leads to this rich get richer effect, because people who have already a very high degree are likely to attract new edges way more than everyone else. And the third part, well, I'll give an example here, but yeah. And this is something we see in a lot of online networks, and this is very old studies have shown that online networks have this like power law degree distribution that can be explained through preferential attachment mechanics. Very few people connect a lot. Most people do not connect that much. So this is just power law fitting to the probability of connection above a certain degree to see that it kind of looks like a power law. There's different statistical tests you can run to actually like test or not test. And there's a bit of controversy of like what networks do have this or not have this, but this is one model to think about it. And the third ingredient that I mentioned a little bit before is homophily. So if people have different labels, red versus blue, the connection that it introduces is only accepted with a certain probability, a parameter rho that governs the homophily intensity in the network. So to give you an example, let's say you start with this network at some time step. There's like people who are connected, they're red and they're blue, and a new node comes in at every time step. And this node first chooses a color, red or blue, with a certain probability. That is the minority fraction in the network. Let's say it chose blue, and it will connect based on preferential attachment. Let's say it chooses some node based on with probability proportional to the degree, and maybe it chose this red node. And now it's going to accept or reject the connection based on the homophily parameter that we mentioned before. If they were the same color, connection would have been accepted. Because they're different, or it might reject with a probability rho as well, right? So, okay, it worked. This kind of model on its own is interesting because it leads to some cool dynamics we can study. First of all, it leads to inequality in the degree distribution of the two communities. I mentioned before that the preferential attachment model leads to this power law degree distribution, where few people connect a lot and most people do not. If you have two communities with this kind of homophily parameter introduced, not only you have a power law distribution, you have two power law distributions for the two groups, and they're different with different coefficients. So here it says the number of top nodes with degree at least k that are red follows a power law distribution with one coefficient that depends on the red community, and for the blue with a different coefficient. And the fact that these coefficients are different is the interesting part, because in this case, actually wanted to, well, maybe it's not. Yeah, so given that the coefficients are different, it means that if you look at the ranking at the top nodes of degree above a certain fraction, it just means dividing these two numbers. So the fraction of minority nodes goes to 0 as you look at higher and higher degree. And that's something that we saw empirically. We saw that in the BLP. We saw that in a bunch of other networks where the minority group representation among the degree just like slowly vanishes. They call this in the paper a glass ceiling effect, which refers to the concept of like as you move higher and higher in the on a particular hierarchy, here is governed by social capital, by the degree itself, one group is just cannot make it above certain thresholds. Here the probability of them making it for higher and higher degree vanishes, as explained by this power law behavior. So with this model in mind, we wanted to see what we can understand, what is the effect of PageRank and HITS on this kind of network as well. So I'll start with HITS, and I want to talk more in detail about HITS. And the main idea, the main theory that we were building for this is a theoretical analysis of how exactly does HITS affect the minority representation in the network. So we use a mean field analysis to do this kind of explanation and this kind of theory. And the main result tells you that you have a graph sequence that's generated from this bias preferential attachment model with homophily, minority-majority partition, and preferential attachment. First of all, what's not that hard to notice and to compute is that the average authority score, on average, generated by HITS is lower for minority than for majority. I mean, same happens with degree. That's already given by the power. That's a weaker result than the power law distribution. But more than that, we can see something more, which tells you that exists this close form relationship between the homophily parameter and this bias amplification as compared to the degree distribution. So in cases of low homophily, the bias actually gets mirrored or reduced, so the representation of minority among the ranking will be basically like the degree distribution, and I'll show you what I actually mean by that. In cases where homophily is moderate, so there is a little bit of cluster structure, then the bias gets amplified, so minorities get further pushed down. And in cases where there's a very strong homophily and the two groups are very segregated, that's where you get the largest bias amplification and minorities really get pushed down at the bottom of the network under HITS as well. So I'll go into details of what this means and how we derive this kind of result. The main idea, as I mentioned, is to use this mean field analysis that basically tells you how do we compute the authority score. It's a principal eigenvector of some transformation of the adjacency matrix of the network A, and computing things with a principal eigenvector is a little bit harder than looking at the fact that it is equivalent to counting the 4 backward paths that, as I mentioned before. So counting 4 backward paths is much easier to do, and we can do that. And the model provides us with the necessary tools. It's tractable, so we can compute the probability of a blue node connecting to a red node through an edge, and from there on, we can further compute the pathways and the probability of a pathway ending up in a red node or a blue node as we go backward and forward. And what we end up is with an approximation of the authority score of a node that is red or that is blue. That will depend on the degree, the in degree. Remember, this degree follows a power law from the model. It depends on the out degree, which in this model is constant. You can have different models with different out degree distributions as well. And it depends on a third factor that I'm intentionally leaving kind of elusive here, and I call it some sort of multiplicative factor. And this multiplicative factor is just some element. You can think of it as some like abstract number that gets computed, and it gets it's different for the red and blue, right? So there's an ugly closed form expression for this. It doesn't really matter what it is. What matters is how it compares between the red and the blue. So what I'm trying to say is that if you look at nodes with similar degree, the in of a node V is similar, depending on how these multiplicative factors compare to each other, the authority score of a red or a blue would be higher or lower, right? Yes.
In this is a directed graph model.
Yeah.
Yes.
Yeah. Yeah.
How is it assume the out degree to be also heterogeneous?
Oh, so in this model, the out degree is constant. At each time step, a new node comes in and it forms a constant number of edges. But it could be different. I would be curious to see an analysis for a different out degree. Yeah.
Because that's also important for the calculation of HITS. Right?
For sure. That's important. Yeah. We haven't really analyzed for different models on that. Yeah. So let's look at this multiplicative factor. Basically, the analysis is giving us some tools to compare these for different communities, right? So if these two factors were equal, you would just end up with the degree distribution, because whatever happens in the degree distribution would happen in the authority score distribution as well, and the ranking will be preserved. However, if the, say, multiplicative factor of the blue community is higher, that means the blue nodes kind of get pushed up in the ranking compared to the red nodes, right? So it really matters the relative value of how these two terms compare to each other. So we can just look at the fraction, and if the fraction compares to how the behavior of this fraction compares to, say, 1, and analyze its behavior as a function of the model parameters, which are the homophily parameter rho, the red and blue communities, and the minority fraction little r there, right? In reality, we work with something that goes over time because this network evolves at every time step little t. It's not that bad to analyze this as a function of time, because the key part of the proof is to analyze this function as a function for a couple of time steps. So basically like a couple of iteration of this backward forward path. And then we can use induction to show the exact same behavior of the function as well. So the main result for the behavior of this fraction is that it's increasing and it's between 0 and 1. And that tells you, you can analyze more things about it, exactly how it's increasing and so on. But I just want to show you this, right? So if you look at the function of the parameter rho, which is the homophily, near the 0 axis, that means you have very segregated networks, and near the 1 value, you have very integrated networks. And the y-axis is just the fraction of the these multiplicative factors for the red and for the blue community. So what it means when it's equal to 1 at the top right corner, it just means that this fraction is equal to 1. So whatever ranking you get in the in-degree distribution, you will get in the authority score as well, right? So nodes of similar in-degree who also have the same constant out-degree have the same multiplicative factor, so the ranking doesn't get affected. It means that the ranking provided by HITS is the same as the ranking provided by the degree distribution. Remember, the degree distribution is our baseline. It's our societal inequality. This is our starting point. It got formed by some process that we modeled. And what we care about is to see how HITS, I'll show you PageRank too, made that better or worse. Did it amplify inequality, or did it make it the same? Did it make it better? And this is just saying it mirrored inequality. So under very integrated networks, HITS doesn't have an effect. It just mirrors whatever social inequality you have in the degree distribution, right? And yes, the rho on the x-axis is the homophily parameter. On the very near 0, these are very segregated networks. Near 1, these are very integrated networks. So there's no homophily in a sense. This would be like 2 different clusters that don't connect to each other. And here you'd have 2 integrated groups. Like imagine an Erdős-Rényi graph where some people are red, some people are blue, but they have the same probability of connection with each other. Sorry? Oh, no. 0.5 would be somewhere in the middle where you have some separation of the clusters.
No, neutral is like you consider them the same as zero.
The same as your 0 would mean that if I'm red, I never connect to blue. I'm completely segregated.
And the other way around is like kind of
I don't care. I connect with everyone in the same with the same probability. No. The only thing that governs the dynamics is the preferential attachment. So you're still going to connect with people with higher degree, but what color they have in their label does not matter to you. Yeah. So at the very left side, these are super integrated networks. They don't really have homophilic behavior. And these are the cases where an algorithm like HITS mirrors societal inequality. At the very left side, these are the super clustered networks where HITS gets way far worse than degree. And what I mean is that it pushes the minority down in the ranking that it provides. And having this value of this ratio f of rho near 0 just means that the relative value of mf of r over mf of b is close to 0. So even though initially the nodes maybe had similar degree, the red nodes got pushed down in the ranking as compared to the degree distribution. Yes, a question.
This means that, for example, the behavior that we can observe in Instagram couldn't happen in this one. Like we couldn't have that the minority get pushed up. Like it's
Yes, exactly. So that's a good point. In this kind of model, this kind of model leads to the fact that because you have a minority with this model, the minority is always disadvantaged in the degree distribution, right? And Instagram was this like funky case where the minority had a better degree distribution. And one way to adapt this model to explain that behavior is to create different homophily parameters for the minority and the majority. That's something that Instagram has. A super connected and homophilic minority actually can reverse the degree distribution compared to the majority. And when that happens, all the trends get reversed as well. HITS will make it better for the minority, will amplify whatever advantage they have to. The fact that they're a minority or not is not really the main thing. What matters is whatever degree distribution they have. Whoever has, in a sense, the best social capital in terms of the degree, that is the group that wins in the end. And that's why I also show Instagram, because this kind of model is a good start, but not all networks have this like heterogeneous homophily among the two groups. And Instagram is interesting because it does follow the trends with a very slight modification where the two groups have different homophily. And that's a good point to add. Where were we here? So yeah, oh, I could have just gone here. So let's come back to the empirical trends and see how the theory explains some of them, right? So on the APS data set, this is a highly homophilic data set with the two kind of segregated groups. There are two different subfields of physics. They don't talk to each other that much. And there's some inequality in the degree distribution in the orange line. It got made really bad by the HITS algorithm. And it actually made kind of fine almost by the PageRank algorithm. So PageRank had this opposite effect. And we explained that in the mean field analysis by the fact that instead of doing forward paths in PageRank, you do backward forward path. So it somehow like aggregates the issue that the minority is more disconnected. DPLP data in the middle had this like very low homophily, was kind of integrated. And that's where both, like everyone kind of does in the same, all the algorithms kind of do the same. So there's some inequality by degree. It gets mirrored by HITS. This is what the theory explained as well with this top point here. So this is where DBLP would lie, and this is where APS would lie, right? And Instagram is this interesting case where it tells us like adapt your model. If you adapt it by a very small modification with differentiated homophily, you can explain this trend. A minority group, I mean, they're almost kind of equal. They're like, what, 46% minority is really not that different than the majority, but they have a higher degree distribution, as you can see by the orange line. That degree advantage gets amplified by HITS and actually kind of reduced by PageRank. So kind of the opposite view of what we saw in APS as well, right? Yeah.
I was thinking that you don't allow for the model to generate potential images.
To generate what, sorry?
Like the opposite, I would prefer the other group more.
That's right. This is a purely assortative model.
I was thinking maybe that the top, I also think how that would but I was thinking, let's say if you had a dating app data, that's like fully different. I think the result would be very different.
Yeah, exactly. I think so too. It would basically tell you that, yeah, I think a minority that connects very highly with majority would be the advantage one. And I think that would actually be a way in which we reduce it to this kind of case. I don't think it matters that much the absolute value of how disassortative you are in the network. I think it matters the relative value between the two groups. So if me, the minority group, want to connect way more with majority group, then they want to connect with me. I think that difference is what matters. So we can call that disassortative, or we can call that homophilic, but with different values. It would be, yeah, that asymmetry, I think. Would, yes. The homophily metric? Yeah, good question. So here we basically compute it's called a verification index. It tells you like what is the percentage of edges that are connected with the same community over the expected number of edges that I would have within that community under a network model here, a completely random model with n nodes. So that tells me like by how much more am I connected in the real network with people similar to me than I would have in a random network. And that tells me if I'm like homophilic or not homophilic or less homophilic.
This is called verification.
Verifying index or verification index. I will find it in the exact name in the paper. Yeah. I mean, I think that's an interesting question in general, because estimating homophily in the network per se is not obvious on how to do. And there's different indices that tell you like this is what it should be, but it's not obvious at all. Great. So yeah, the reason this was also interesting, it related to a lot of the early theory on HITS that came out right after this algorithm was introduced. And this theory just told you like completely disconnected communities are going to fare really badly in HITS. Don't use HITS for disconnected communities. It's going to do terrible. They didn't tell us much though about this more subtle effect when the communities are never really disconnected. There is some homophily. Maybe there's a lot, maybe there's less, there's moderate one. But what happens then? I mean, how bad is HITS going to do? And this kind of theory provides you with this continuous relationship between homophily, and community structure, and bias in ranking algorithms, which, as I mentioned, we explained through the inequality in the degree distribution and this homophily parameter. So what about PageRank? Let's come back to it shortly. We've seen a bunch of like numerical and basically this empirical results, and like PageRank kind of does the same, but kind of has this opposite effects of HITS, and that's interesting. And one way we thought about it in the same like mean field analysis that provides some evidence for like you're counting forward paths instead of backward paths. There's a recent theory that that came out as well to tell us exactly what the PageRank distribution is, which is stronger than a mean field analysis. And we were working on adapting this kind of theory for HITS as well to tell us something about the distribution. And I'll tell you a little bit about what this theory said. So until recently, the PageRank distribution of a power law network, regardless of communities, we didn't know whether it's a power law with the same coefficient or not with the same coefficient. And a theory showed that actually, well, it is a power law, but it's with a heavier tail. And then this follow-up work in 2022 showed that the PageRank distribution of, this is the word that I mentioned, right? So if you have a degree distribution, then the PageRank distribution is also a power law, but it's not the same power law. It has a heavier tail. And the heavier tail contains as a parameter, the coefficient, the restart probability. And that makes it heavier. And only, last year, this work came out with very interesting and heavy theory on continuous branching processes in networks to show that in the bias preferential attachment model with two communities, the PageRank distribution is also a power law, but it's with the same coefficient, which is interesting because we started with the degree distribution with different coefficients. And they say, well, actually, PageRank makes a distribution with a power law distribution with the same coefficient, right? So this is some evidence that was found to say, well, yeah, I mean, PageRank will, in some cases, make the distribution a bit more equal. It will improve fairness in some cases, especially in these high homophily cases that we saw in APS, for example. Of course, the constants matter in front of the power law too. So we also saw that in some cases, well, PageRank is not fully fair. It just kind of mirrors whatever distribution you have. And there's some open work of exactly what is going on there. There's some assumptions that go into this kind of theoretical work, I mean, just like in ours, and those rely on computing the distribution of the most connected node and then having a local limit argument that other nodes would also follow a similar distribution as well. And that's how you get this power law. Empirically, the BLP is a case where that wasn't the case. Right, so that something tells you like either the model is not really fitting the real world that we see. There's some open questions there that we can further investigate with respect to PageRank as well. And similarly, the work that came out from this lab also a couple of years ago showed that, well, there is some bias on the PageRank distribution as well. If we look at measures of equity or inequality as measured by Gini index as well on different kind of networks that are similar to this bias preferential attachment model as well. So it's not like PageRank is the answer to everything. There's a lot of interesting questions there with respect to fairness as well. But I wanted to give you an overview of this kind of methods that we've used and other people have used to study these questions. So Future directions can think about bias with respect to the constants themselves in front of the power law. The power law gives you this like asymptotic result also when the network tends to infinity, right? It talks about the stationary distribution. There's a bunch of other future directions that are open here to think about. We've explored a couple of them. Many of them still are open. So HITS doesn't have randomization restart in the same way that PageRank does. What if it would? That would be interesting, right? Like, does randomizing actually help if you restart the pathways that you're taking, the random walks? And you can do that. I mean, people have tried this variant in the past. They haven't analyzed it theoretically, so that's something that we were doing as well. And if you do these random restarts with some probability E, and then you start from the constant vector as well, then it basically tells you that, well, this is going to follow the degree distribution. So it's not going to make it better. It's not going to make it much worse. The same mean field analysis theory tells you that it will be close to the degree distribution. You can think about other directions. So the other one that we thought about is like, okay, so HITS is basically this principal eigenvector of this adjacency transpose adjacency, right? Like this one ATA matrix. But that's just the top vector. The top vector should contain the most information. You can think about the subspace spanned by multiple eigenvectors of this matrix as well. So again, people have thought about this application as well as what would happen. We've studied it in a variety of networks as well. There's open theory about this. I don't know what happens and how to do this properly. I think if you just take K components, basically, and you can aggregate them together in the authority score instead of just the top component, you can do that in a variety of ways. For example, weighted by some function of the eigenvalues lambda I, and this is just the eigenvectors VI with the basis vectors, the orthonormal basis. You can choose F to be identity, can be square, can be really like a variety of options. And you can try out to see how to combine different components. We try by combining just like the top K components for varying K, like how many components do you actually care about. In practice, this varies a lot depending on how many components you choose. It's not even clear you should choose top K components or particular ones that actually contain signal. And how do you find them? What's the signal? I don't know that question. I think that's an open question. But I'll just show you what it looks like if you choose different number of components from 1, 2, 3 up to like 10. Results vary greatly in terms of fairness, right? So the purple one is just the original one that in HITS, let's say we're looking at the right on the leftmost side on the APS data set. So it just like went to 0. The orange was the degree, and everything else is like all this crazy stuff with different components that we see here. So this is also for the APS when you choose this weighting function of the eigenvalues to be 1 or lambda squared. Results kind of vary, and some of them make you a little bit more fair, so closer to the percentage of the population in the network as well, which was 30-something%. But some of them don't. Some of them mirror exactly what you had originally. So it's a bit of it's an interesting direction, a bit chaotic to study. I'm curious to know if this kind of subspace, which reminds us a little bit of the way PCA works, and there's some work similarly on like how to choose fair dimensions for PCA that actually improve the representation of different communities in PCA. But this is a little bit different, and I don't know how to solve this theoretically. I'd love to hear thoughts on that. Similarly for DBLP, here you see also this interesting trend of like you choose different number of components, you can be super fair, you can be kind of unfair. So it really ranges everywhere in this space. And same with Instagram too. So and future directions more broadly, just a couple of minutes on that, and then I'd love to take more questions and feedback, is that, so this kind of work thought about what are methods from networks that we can use to identify and diagnose when algorithms are unfair, like HITS and PageRank. It's a diagnosis method. It's not really intervening. The subspace stuff is a bit intervening, but it's not providing any particular like interesting interventions. And I've been thinking about kind of these two directions, what methods we can use to diagnose inequality and bias, and what methods we can use to intervene on it in a way that make things better in different applications. This was the one in ranking. I think about intervening methods in a variety of applications. The most recent ones that I've been working on are on social influence maximization and how do you design campaigns in which you want to maximize the outreach based on a few select people, and that becomes an optimization problem. And we think about using optimal transport to make the distribution of outcomes equal among different groups. And similarly, we think about more broadly, I've thought about how do you compute actually the space between different objectives that you have. Let's say you have efficiency. We thought about this in the case of clustering, where the efficiency metric is some NP hard objective in clustering. And the other metrics that you may think about are fairness, perhaps, statistical parity that you have among different clusters, and so on. And what is the optimal trade-off between them? Right? So how knowing this trade-off, the actual Pareto front, allows us to probably intervene in the right way. If you have like a big trade-off, small trade-off, allows the decision maker to choose the right policy there. If there's not a big trade-off between fairness and efficiency, they'd rather be improving fairness in that case. And computing this is a hard problem because, well, clustering is hard, it's an NP hard objective. We can have some approximation results there based on the approximation algorithms that we know in clustering too, and we translate that to different objectives, to this multi-objective problem in fairness and clustering as well. So these are two submitted works. One of them is online, the other one I'm happy to share, and it will be shortly too. But that's all I had for today. So thank you so much, and I'd love to hear questions.